How have you been getting on this week? Does anyone have anything interesting to report? Anyone been writing any interesting software implementations? Have anyone found anything interesting out? How's it been this week?
I don't know about other people, but this week has been very, very busy. But I haven't done enough. Computation, but I have been doing a fair amount of logic, because propositional logic, even though we've done it before, saying that we've done propositional logic at university before is a little like saying we did arithmetic in year 9 GCSE. It's yes, we have a little bit of syntax, but we don't have a lot of the ecosystem, the way that things are done, how they're done, why they're done, what's been done before, kind of ideas.
Okay, good. So been doing the reading then, the propositional reading. Okay, nice. And how's everyone getting on with lambda calculus interpreters at the moment? Everyone happy with that?
Yeah.
Yeah. So again, we can take some.
Yeah, I'm just trying to design interpreter like by using Python like that. Just a simple number. If I I would like to show you my work if I can. Just like,
sure. Yeah. I'll just make you a presenter.
Yeah. So just in my first time, so how should I do to just to share my screen?
Yeah, if you click the purple icon in the bottom right, and then you'll see a sharing icon appears, which is a box with an arrow coming out of it.
Okay, I'll try. Oh, shit.
Just while you're getting set up, a couple of people have been asking me about the portfolio assessment. You will notice if you look at the portfolio assessment, which is on the Blackboard site, there are 2 questions on it, and question 2 is about these lambda interpreters. There is also a question 1, which is about logic. So we haven't started to look at question 1 yet.
Okay.
But they're actually numbered in the opposite order. We're doing question 2 first. After Easter, we will talk about question 1 and help you to get set up for doing that assessment. So it's all about assessment question 2 at the moment.
I don't know if now anyone can see my screen.
Yeah, we can see it.
Okay, just I think it's so I'm just trying to mostly my program I think can solve the most of the lambda expressions like that. So I will show you just trying to, and I post some of the examples in the notes, so it's easy to import like that. So just my because of the for this expression is it's a simple expression just with 2 sub expressions. So my program just try to it will just the main algorithm is is here. So the program will try to split the whole expression into the 2 sub expressions, and then it will check if it needs to have like the alpha conversion, and if needs it will just implement the alpha conversions by what I've done like that here. So it's all things about the alpha conversion. Just it will check if it has the same variables in both expressions. So it will try to replace one of the symbols into like the because I've just used a symbol algorithms, like I use ASCII like so if it's also I will just show you like if you need like this expression. Oh yeah, it's infinite. So for this expression, because the second sub-expression has same symbol, which is x, like that. So it will because x when we convert into the ACCI number, it will be like 100 or anything else like that. So it will check if it's like the final letter like C, so it will be converted to A. Else it will just add one like the A, like the it will be converted like the B or C, like the following like that. So, but I found a very challenging thing it's hard to check if the expression is infinite, so for this expression, it cannot be reduced at the end. So just I would just have iteration for 10 times, I think, just for 10 times, so it will be stopped.
And so you automatically stop if it's taking too long.
Yeah, but I've checked one thing like the x, so just for this example, like for this example, because this one is very simple, because when we put the second sub-expression into the first, and then we will get the same results as like before. So just I will just check the if it's the same result, like if the second beta reduction is same as the first input, or anything, it will be just stop the program and post and print
yeah. So in some cases, you can tell if the thing is going to not fail.
Yes, yes. I've just tried my best.
Yeah, very
so.
nice. So how do you do the parsing in your version then? How do you take the string and turn it into a tree structure? Could we see that part of your code?
Take the string into
So are you doing lexing and parsing? So you're reading in that string of the expression.
Yes.
And you're copying it to.
Yes, it's this part.
Here's the parser. Okay.
Okay. Yeah, and because I'm just try to because I will just split it like it totally have three situations. So I just use the if else, because some of the lambda calculus, like the lambda calculus expression, when we use the beta reduction, so we have the for this one, like when we first use the beta reduction, the result will be here. So it will be so it will there has a one lambda expressions in the another one lambda expression. So it will be like here. So for this case, I will just use one algorithm for solving this case, and another algorithm for just solving like both have two how to say it's two lambda calculus and just like the simple lambda calculator expressions.
Yeah.
And
so here you're acting on the string itself, aren't you? You're maintaining the expression as a string, and you're changing symbols in the string. I think.
yes.
Yeah. Okay, interesting. So this is a different approach, say, to Matthew's system that we saw, where we're interpreting each part as an object in a class, object.
Yeah, because I just just according to the reference like you posted on the Blackboard. So I've just if has like the three. So my program already always solving like from from the left to right, like it will just take the first two expressions and solve it, and then just combine with another like the third sub expressions, and then solve it, and then just keeping
And
it.
does this still work if you get very heavy nesting of brackets?
Yeah.
That would seem like when you might need a more hierarchical structure than just operating on the string. Have you run it on any complex expressions with lots of nested brackets?
I haven't tried it because I would like to just write some expressions and just solving by my hand, and I will just check the program like if it has the same result.
Yeah.
So,
Okay, excellent. That's really nice to see, and it's an interesting approach.
Yeah, no, that's really cool. That's it's deceptively like simple. And as for nested brackets, this solution actually it only really needs like one change in order to be able to solve that, which is when you're searching for the ending bracket, it's just account for the possibility of nesting. So yeah, that's really good. That's deceptively simple. That's really cool.
Thank you. Yeah.
And I have to say your Python code looks much more beautiful than Matthew's C. As Python code often does. Even though it's natural, the Python is still pretty.
Yeah.
Okay, good. So we can talk some more about lambdas in the workshop session. Oh, you guys need the code, don't you? Let me find your attendance code before we start. Give me one moment to find the register code. So today is the 24th. Okay, so there are two access codes for today. Here's the lecture code, and here is the workshop code pasted in the chat. Can everyone see those okay? Any problems? I suppose the great thing about lambda calculus is because we have that Church-Rosser theorem. That theorem says it doesn't matter what order you do the evaluations in. So yeah, maybe in these string-based approaches, maybe you can always just pick off the next evaluation to do that is the easiest, syntactically the easiest to do. And as long as you go around doing one beta reduction every time, you'll be guaranteed to get to the right answer. You'll get the same answer as if you did the evaluations in a much more difficult order, where you really have to keep track of the bracket. So yeah, I'll be very interested to see how that holds up when you get to complex nested expressions. Okay, good. Really nice to see everyone's code. So we have covered the basics of computation theory now. We've looked at lambda calculus. Last time we looked at Turing machines. We found out they're equivalent. They're two different models of the same thing, and they both end up with this notion of the halting problem and this notion of some problems are uncomputable. And we talked last week about how they lead you to different styles of computing. The lambda calculus leads us to this very functional view of the world, and the Turing machine leads us to the C view of the world. So I wanted to make a start talking about logic today. When we get to the second half of the module, we're going to look more at applications. So I wanted to show you what some of this stuff is actually for. But just in case people wanted to think over Easter, really, more about logic, I thought I'd put in some first round of logic this time, and then we'll do another round of logic when we come back, and then we'll do the applications. Normally, when we talk about logic in computer science, we are talking about what is called first order logic. That's the logic where you have the upside down A's and the backwards E's. And it can get quite hard. The traditional approach, which we are going to follow to get into first order logic, is to first study what is called propositional logic, which is a subset of first order logic that doesn't have the upside down A's and the backwards E's. It only has ands and ors and not, pretty much. So probably you think you have seen this before. Maybe you think you know it all already. As we've hinted at earlier, there may be a little more to it than what you've seen before. And in particular, if we labour some of the points today, if we seem to be going into a lot of pedantic detail, it's because we are going to introduce a bunch of concepts that show up in these other logics as well. So you may think it is overkill to study propositional logic to this extent, but the point is we're going to meet all these concepts, and then the same concepts show up in every logic. They show up in first order logic, they show up in the modal logics, for example. Remember, modal logics are these logics of possibilities and necessity. The program could get into an error state, or the program will definitely get into an error state. So any logic you choose to work with will have these same basic ingredients. And by studying them first in the context of propositional logic, it's easy to understand what's going on, because hopefully you've all seen basic propositional logic before. You know what it is. And so when we introduce these ideas, they're sitting on something we've seen before. Then when we go to the other logics, they should all make a lot more sense. So as with any logic, we are going to split up our study of propositional logic into 4 components. And these are the grammar, the proof theory, the model theory, and the meta logic. So we've talked about the meanings of some of these before. The grammar in this context means the syntax. It means the set of symbols that goes into the logic and the ways you are allowed to combine them to make up formula. That's independent of any meaning of the symbols. That's purely writing down strings of symbols. When we go to proof theory, we then introduce rules for manipulating those formula. And we have this concept that some formulas are theorems and other formulas are not known to be theorems. Now, the rules of proof theory, we've seen things like all men are mortal, Socrates is a man, therefore Socrates is mortal. We will see the equivalent of that. We're going to see a set of rules for manipulating formula, which allow you to produce new theorems from old theorems by combining them together. As with grammar, there is still no concept of meaning at this point. We are still just manipulating strings of symbols when we do proof theory. And you can happily go and do proof theory without ever worrying about what the symbols mean. You're just starting from one string and trying to get to another, and then you call it a theorem. To talk about the meaning of the strings, we then go to what is called model theory, otherwise known as semantics or representation. Logic is a big subject, lots of different people study it, and they all give slightly different names to the same underlying idea. So in model theory, we will finally see how to give meaning to a string of symbols. We'll see how to create a mapping called a structure from those formula to actual things, either things in the world or other abstract entities, usually sets or numbers or something like that. So model theory is the point where you can start talking about the values of formula, whether a formula is actually true or false. In proof theory, you're saying that a theorem is provable if you've arrived at it. In model theory, you're saying whether or not that statement is actually true relative to the thing that you are representing by the logic. So if your world consists of 3 people and 2 of them are tall and 1 of them is short, that's your actual world that you live in, and it is true that 2 people are tall. If you end up with a formula which is supposed to represent the claim that 2 people are tall, you can now say the formula is actually true relative to the structure that you're using. Then finally, we will talk about the meta logic. So we've met meta logic in the context of Blender calculus already and Turing machines. This is where we step outside of the system, which in this case is propositional logic. We're going to step outside of propositional logic and we're going to look at facts about the system. Ideally proven facts about the system. So these are things like whether the logic actually works. Can you ever get the logic into a state where everything is contradicting each other, or can the logic be broken in various ways? So that's the plan, right? We're going to do grammar is the syntax, the symbols. Proof theory is the rules for manipulating symbols. Model theory is how to give meaning to the symbols, and meta logic is proving stuff about the system, which is usually checking that it actually works and does what you think it's going to do. Okay, so once again, propositional logic is supposed to be easy. It is here as a simple case study of a logic, and later there will be other logics which are more complex, but they'll always have these same structures. So let's talk about the grammar for propositional logic. Ultimately, we are producing formulae that look like this. So you've almost certainly seen stuff like this before. Where have you seen formulas like this before? What else have you studied?
In logic.
Mm-hmm.
So obviously different kinds of logic. So we have done propositional logic, but we've also done Boolean logic, and you use the same ands and ors and nots. So that the syntax is comparable.
Okay, good. So what's the difference between Boolean logic and the logic that you see in AI, for example? Why do they have different names?
Well, Boolean logic, the central concept of Boolean logic is like it has a more reduced set of things that you're going to be able to say and do, whereas propositional logic almost matches quite one-to-one with that what we were talking about on the other day. So a more like humanitarian type style of statements and logics.
Okay, okay, good. So, just to recap then, can anyone read this out to me in English? What does this say, translated into English? Just the first one.
Anyone else?
A and B.
Okay, yeah. So this says A and B, yeah. And what's this? Or, yeah. So that symbol looks like a letter A for and. That's how you remember it. And that one doesn't, so it's or. Okay, good. And then what's going on here? How do we read this part?
Not C and D.
Not C and D. Yeah, that's right. And the not only applies to C. Yeah. You could also read this as D and not C. That would be different from not C and D. Yeah. Okay, and eventually these things are going to mean things. Eventually A is going to represent something. What kind of thing is A going to represent? Or what could it represent?
Well, it
Like
represents another theorem.
But ultimately, we want to use these formulae to talk about some actual stuff, right? So, could A be a car? Or could A be a sheep?
Yeah, I think so. Like Matthew noted, it could be the sun is shining, or it is raining. Maybe a statement or a sentence in that sentence.
Okay. Yeah. So what's the difference between a sheep and the sun is shining? So can A represent a sheep?
That's interesting. I think that's actually one of the big differences between propositional logic and Aristotelian logic is a sheep is we're setting it up as an axiom or a premise. So we're saying, well, there is a sheep, and then the statement, the sun is shining, that already presupposes that sun and shining are things, and then we're making a relationship between the two. So that would be a statement which we use one of our propositional symbols in order to combine the two.
Okay, good. So in this logic, the symbols don't represent things. They don't represent physical objects directly. They represent facts. The facts can be about things, but there's no concept of a sheep in this logic. A could represent there is a sheep, or it could represent my sheep is black. A and B could represent my sheep is black and the sun is shining, right? But the meaning of these symbols is going to be facts about the state of the world. The symbols don't refer to entities in the world. They refer to facts about the world. Okay? So that's going to be different in some of the other logics we come across. Okay, where else have we seen this kind of logic? What else have we represented in the first year with symbols like this?
I mean, if we're talking around something like Boolean logic, we could talk about logic gates and hardware.
Yeah. So this formula could also represent something like this. It could be A and B, and here's a physical logic gate. Yeah, and then that's going to go and get ordered with a bunch of other stuff. C, sorry, not C. There's a little not gate and D. Yeah. So this is a different way of reading the formula. You know, one way to read this formula is a claim about my sheep being black and the sun shining and a bunch of other things. That is a statement about the world. This way of reading it is a statement about a particular bit of the world comprised of some physical computer hardware, comprised of a bunch of logic gates. And again, think a little bit about the differences in those meanings, right? In the first case, you're asserting something about the world. You're saying, my sheep is black and the sun is shining, and this is the way the world is. Okay. If you look at it as a description of the logic gates, you're saying something a little bit different, because in this reading, A, B, C, and D could all take different values. Okay, each of these wires can be high or low. And you're actually describing a pretty complex collection of possible worlds. How many possible worlds are there in this structure? So each of the inputs can be either 0 or 1 in digital logic.
Yeah, so it's A gives 2 possible worlds, then the input of B is times that by 2, so we have 4, yeah. And then C means we have 8, and then D means we have 16 possible worlds.
Yeah, so here you're talking about 2 to the 4 equals 16 possible worlds. Okay, so in AI world, you'll tend to look at something like this as representing that kind of combination of facts. You're saying there's one world that we're in, and here is a description of it. Okay, we are in a world where all of these things are true. The sun is shining, and my sheep is black, and that's the world we're in. But in this digital logic reading, we're talking about the whole collection of those worlds together. Okay, good. We jumped ahead of ourselves a little. We're supposed to be only talking about the grammar, right? So grammar comes before any of those meanings, but it's nice to see some examples up front. Okay, these strings then, these are just strings of symbols at this level. They don't actually mean anything yet. We are only allowed to write down certain types of strings, and we call these strings formulas. Okay. Different books use different words. If you're is this Latin or Greek? Whichever it is. If you're a real traditionalist, this should be formulae. If you're a real traditionalist, this should be a special little LaTeX thing with the A and the E joined together like that. I think modern books are pretty much standardized on formulas as the plural. You will also see them described as well-formed formulas. That just means the same thing. Often that is abbreviated to WFFs, well-formed formulas, and that may be pronounced WFs in discussions. But I think the modern take on it is just to call them all formulas. What's the difference between a formula and a theorem? Okay, so for example, if I write A and not A, this is a formula. It's generated according to the rules of the grammar. But this is hopefully never going to be a theorem, because you hope that the theorems are things that are representing true statements about the world. And it's never going to be possible for A to be true and not A to be true at the same time. So you hope this is never going to come out as a theorem, but it's a formula. And along with these things down here, it is a formula because it is generated by this set of grammatical rules. So we've already seen these for the lambda calculus, at least. Here is a grammatical rule for generating variable names. Okay, well, in this presentation, we will assume that a variable name can be one or more lowercase letters. Okay, so A is a variable name, B is a variable name, ABC is a variable name, foo is a variable name. Okay, so this notation means any character in this range, and the plus means repeated one or more times. That's a standard grammatical notation. So once we have defined what a variable name is, we are then going to describe what an expression is. And the expressions are what is meant by formulas in this case. So a simple expression can just be a variable name. Okay, so if I just say A, that is a formula. A could represent one of these facts, the sun is shining, or it could represent the state of a wire going into a logic gate, or it could represent many other things. You can also take two expressions and combine them together using an AND symbol, and you can do it using an OR symbol. So here you can say A and B, and I'm being very rigorous on this slide. Like we did with the lambda calculus, I'm going to insist that we put brackets around everything to clear up any ambiguity. So this is a formula. You could write A or B as a formula with brackets around it. And finally, you can take an expression and you can negate it by putting a not symbol in front. So not A is a formula. Okay, and all of these are recursive, so you can take any expression you've already created and use it as an input in one of these rules. So for example, we can apply this rule, and we'll take two expressions we've already made, such as A and B. Let's take that one that we already made, and I'm going to use that as the first expression, and then let's say not A. We've already shown that that is an expression. I'm putting the brackets around. Now we've created another expression using this rule. And so that's how we generate formulas that can look like this. As with lambda calculus, the brackets will very rapidly get annoying for any practical purpose, and so we will apply some human syntactic sugar conventions to reduce the amount of brackets. And you're probably all familiar with what these are. Okay, there are standard things like that not C, we're just going to write it as not C. And if we see something like not C and A, the convention is that that not symbol has a higher precedence than the and symbol. So it's assumed that you are going to rewrite those brackets and add them in there. And when you see an and symbol like that, you're going to assume that there are brackets around there later. So as an optional exercise today, we might talk about how to write interpreters for propositional logic. And just as with lambda calculus, you may need that syntactic sugaring step first. If someone gives you, not C and A, maybe the first thing you want to do is just put the brackets back in to desugar the thing, and then it makes it easier to see what's going on. So is everyone happy with this structure for generating formulas of propositional logic?
Mm-hmm.
Okay. There's a symbol missing actually that is sometimes included, or you can define it out of the other symbols. What's the other symbol we often see in propositional logic? Well, this little arrow, yeah, the right pointing arrow, yeah. And I'm not going to pronounce it as therefore or as anything. I'm just going to call it an arrow for now. So yeah, you'll sometimes see expressions like this. So it's possible to define this out of the other operators. Anyone know the standard definition for this symbol?
I just call it, when I see it, I think if, but not if, and only if. So yeah. If with one F.
So it's not normally pronounced as implies when we do this kind of logic. Yeah, it means something like, oh, good question. It rules out only one possibility. It means it's not the case that you can have A without B. Does that make sense? It's saying if A is true, then B has to be true as well. So you're not allowed to have A on and B off. But you are allowed any of the other combinations. And that definition is controversial because it doesn't quite correspond to the human notion of causality or ifness. And that's why we have to be really careful just to treat it as a symbol at this point. Okay, so that's what propositional logic is. That's what it looks like, at least. What are we going to do with it? What kinds of questions can we ask a propositional logic system, or what kind of questions can we ask about the propositional logic system? So, the simplest questions to ask are questions that use propositional logic. We are going to use those symbols together with some rules, which together describe the logic. And there are really two main questions we would ask. If I give you a theorem, if I tell you that this is a theorem, can you find a proof? Can you explain why it is a theorem? Or alternatively, if I give you a formula, can you tell me whether or not it is a theorem? So maybe this is going to be the easy question, because here I'm giving you some extra information. I'm telling you this thing's a theorem, but I'm asking you to explain why. This is a harder one because you don't know in advance whether there's going to be a proof or not. So why might it be easier to show that something is a theorem rather than to show that something isn't a theorem? And when have we recently done this?
Oh, that's what Gödel's talking about.
Okay. When have we done a really simple version of this in this module?
Well, this is
MIU system.
Yeah, MIU system. Yeah. So showing that MIU IU, is that a theorem? Is that a theorem? Can you remember?
yes.
Yes, I think it is. You can add a U after an I.
Okay. So showing that something is a theorem is pretty easy. Yeah. Showing something isn't a theorem took Gary at least 4 hours of trying. Yeah. Before you kind of got an idea that it might not be, but weren't quite sure why. Yeah. So showing things are not theorems tends to be a lot harder than showing that they are theorems. Okay, so if we go beyond the proof theory, so this is called using proof theory, when you use the rules of the system to derive theorems. We can start asking questions about the propositional logic, and we can do that using model theory and using meta logic. When we go to model theory, now we're talking about what do the symbols mean, and what can the symbols mean, or what should they mean. Hand from Gary.
So as I remember when looking at this, that I think it was when we were looking at logic gates, that you could have a large system and you could simplify it and you could end up with a smaller system. Is it the same sort of idea? Could you find a proof, but then could you also say that, okay, this proof is a more complicated proof that is a simpler proof over here somewhere? If that does that make sense?
So you'll type of thing. Yeah, you might find a very long. In fact, you did this in your MIU system, I think. You had a very long proof of one of them, and then you found a better one, and it was better because it was shorter. Yeah. Yeah. So sometimes the theorems will correspond to interesting things. Sometimes the proofs themselves will correspond to interesting things. So later on, we'll talk about this duality between proofs and programs, and certainly if you're creating a program, you usually want it to be short because it's more efficient, less buggy, runs faster. yeah, so finding the shortest possible proof of something is often an interesting question. Okay. So yeah, what can or should the symbols mean? You know, does MIU actually mean anything? Could M be a thing, and I is a person, and U is a car? You know, could MIUIU represent some state of the world where there's two pedestrians and two cars queuing up to a traffic intersection, and somehow this logic is going to help you say interesting things about that state of the world? You know, there are bigger questions, more general questions. You know, can the symbols of a system actually mean anything at all? Is it possible for a logic to exist that just can never have any coherent meaning? You know, or is there only one meaning, or are there multiple meanings possible? So yeah, we've touched on this already with the propositional logic. You know, one way to read it is this AI style, where it's describing a current state of the world you're in. You know, the sun is shining and my sheep is black. Or another way to read it is a description of a piece of Boolean digital logic, where you're actually describing a whole set of states of the world, the inputs and the outputs. And then when we go to meta logic, now we're asking questions about the performance of the system and its limitations. So you know, these questions, if I give you one particular theorem, then I say, can you find a proof? You can often answer that question, especially when a proof does actually exist. You know, if I give you a formula, is it a theorem? You can very often do that. At least if I choose an easy one. But at the meta-logic level, we're saying, are there general solutions to these problems? Are there any formulae that don't have answers to these questions? And from what we've seen in our study of computation so far, we should now be very aware of the existence of these uncomputable problems. So we expect them to start showing up all over the place. Now we know that they exist. If these things can be done, will they always give you the same solutions? Yeah, so this is like Gary's question. Is there only ever one proof of something? Can there be multiple proofs? If there are multiple proofs, are they all consistent with each other? You know, it would be terrible if we had a logic that let you prove the sun is shining and also let you prove that the sun is not shining. Then you'd be in a lot of trouble. So, you know, are all the solutions coherent and consistent with one another? And these correspond to the next three aspects of logic we're going to look at. Right? We're going to look at the proof theory, the model theory, and the meta-logic, now that we've done the grammar. Which brings us to the proof theory. When we talk about propositional logic, we mean logic that is created from these rules, roughly. There are different ways to set up the proof theory and the model theory. So the title of this lecture is Propositional Logic. We'll see things that have extra names when we look at particular ways to instantiate propositional logic. So natural deduction, created by Gentzen in 1934. Again, this is the time of everything being very interesting, right? Two years before 1936. Natural deduction is one particular proposal for how to set up a proof theory of propositional logic. There are other ways of doing this. And all these methods have different objectives. So natural deduction is the nicest one to start with because it is intended as an approximation to an aspect of human reasoning. It's supposed to be a model of how human beings actually think and how humans do logic. So it is deliberately set up to reflect the kinds of inferences that human beings happen to make. So this is different to some of the other systems we'll talk about later on that are completely inhuman. So let's take a look at some of the rules. This isn't the whole set. The rest of the rules are on the next slides. These are some of the easy rules. And we've seen this kind of notation many times before now. Remember, these are comments, okay? This is like putting // in your code or putting a Python hash in your code. It's just giving a name to the rule. It's not actually part of the rule itself. So this rule is called and introduce. This is a rule for bringing an and symbol into your reasoning. So this rule says if you know phi, that's the Greek letter phi, that's the Greek letter psi, as in psychology is spelt with one of those. If you know phi, if you also know psi, this rule says you are now allowed to write down this string of symbols. Okay? Now, it's not entirely obvious that this is doing any work at all. Okay, I'm taking pains not to say if you know phi and psi, because the top would then read phi and psi, and the bottom would also read phi and psi. What the top of this is saying is your beliefs about the world contain two things, and one of them is phi, and the other one is psi. So you've found that these things are theorems already. You've written them down in your list of theorems. And the rule enables you to write down a new theorem, which is these symbols strung together. Okay, so phi and psi here are meta variables. They could be anything. You notice they're not symbols from the grammar, because the grammar only uses the letters A to Z. So, an instance of this rule was if you knew A, remember A is a symbol in the grammar, and if you knew B, you would then be allowed to write down this string of symbols, okay? Or if you knew some huge complicated expression, okay, that's not huge, that's a little more complex. If you knew something like A and B and you knew not C or D, you would then be allowed to write down A and B and not C or D. Okay, so phi and psi can stand for anything. This says if you have that as a theorem, you have that as a theorem, you can put them both together and put this symbol in the middle, and that is now a theorem, and you can add it to your personal collection of theorems to use later on. Does that not make sense to anyone? Because it is quite a weird idea when you first come across it.
It does not make sense. No, that's good.
It does make sense.
No,
we haven't proved that yet.
Oh, of course. Oh no.
Yeah. Okay, this is going to get very complicated later on. Okay, let's come back to that in a couple of slides. Right? So this is called the and introduce rule because it introduces that and symbol into our theorems. If we didn't have any theorems with ands in them, this would be a way to introduce that symbol into our set of theorems, into our personal theorem collection. The opposite of introducing a symbol is eliminating it then. So if you have this thing as a theorem, and this is a set of, it's a string of symbols, or rather it's a whole bunch of strings of symbols because phi and psi are meta variable. But if you've got any theorem in your theorem collection that is of this form, you are allowed to deduce this. Okay, so you're allowed to throw away one of the arguments and throw away the symbol and pick that one. You're also allowed to do it the other way. So there's two different ways of eliminating an or symbol. And so in English you can read this then as if you know phi or psi, you can conclude phi. if you know phi or psi, you can also conclude psi, and you've eliminated that symbol. You've created a new theorem that is simpler than the theorem you had before. So that's how AND works. Now let's look at how OR works. So here we are saying if you know phi, you are allowed to conclude phi or psi. Okay, so if you know the sun is shining, you're allowed to conclude the sun is shining or my sheep is black. That's a allowed inference to make. You can also do it the other way around. If you know my sheep is black, you are allowed to conclude the sun is shining or my sheep is black. So there's going to be a rule for eliminating this symbol that will be on another slide, I think, as well, because it's harder. Here's something we can do with that right arrow symbol that I mentioned. Again, you can define this out of ands and ors and nots, but in natural deduction, this appears as a basic rule, because remember, natural deduction is a system of rules that is supposed to be as human-like as possible, and this is how humans appear to actually think in a lot of cases. So this says if you know phi implies psi, and you know phi, then you can conclude psi. Okay. So again, the top of this means you have two theorems in your collection. You have this thing as a theorem. You also have this thing as a theorem. And you are now allowed to write down this thing as a theorem. And this is called the implies elimination rule, because you started with a theorem that has that symbol in it, and you've created a theorem that doesn't have that symbol. You've simplified it in a sense. Okay, now look, notice at this point we are doing proof theory, so there is no notion of true or false. There are only symbols, right? We're just saying if you can make this as a theorem, if you can make this as a theorem as well, then you're allowed to write down this thing. And no one's talking about the symbols being true or false. They're just symbols. They're just formulas. Well, they start as formulas and they become theorems if you're able to prove them using the rules. So, you know, as we've discussed before, if you can prove something, then we call it a theorem. Yeah, that's exactly like we did in the MIU system. This is different from what we see in Boolean logic, which is all about things being true or false, or 1 or 0. This is just symbol manipulation for now. Okay, so these are the easy rules of natural deduction, and hopefully these make sense, because they're supposed to be a model of how your human brain does this kind of logic. So we need to add a few more basic rules to capture what humans seem to do. And one of them is to do with introducing implies. This is how we're going to bring a theorem like this into existence. So let's say we've proved a bunch of theorems already, and one of them is phi. Okay? Again, phi, Greek letter F, as in philosophy. I think Greek philosophy is spelt with one of these, whereas Greek psychology is spelt with a psi. Okay, so the rule for introducing this then is a little more complicated. We've talked about suppositions before. So when we suppose something, we are going to temporarily pretend that it is true, even though we don't know whether it is or not. And we're going to denote that by opening a square bracket, or in other ways. Sometimes it's done with indentation. Hofstadter likes indentation. I'm going to use the square bracket. So what we're saying here is I'm going to suppose that phi is true. So I don't know in advance whether it is or not. I'm just going to assume it. I'm going to make a supposition. from that supposition, I'm going to do some inference. So here I'm going to apply lots of existing rules that I've abbreviated with ... I'm going to use the logic I already have, and I'm going to try and deduce psi. I'm going to deduce psi from phi. And at that point, I'm going to close the supposition because I've finished. Now, if I'm able to do that, if I'm able to make a proof that begins with psi and ends up, so which begins with phi and ends up with psi, then this rule says I'm allowed to write down this string of symbols. I'm allowed to write down phi right arrow psi. So again, we were talking about what this symbol actually means. Okay. When I wrote it down before using true and false values, that we'll see more of that when we talk about the model theory. This is a way to introduce it purely using proof theory. So there's no concept of true or false here. We're just saying if I can make a proof that goes from phi to psi, then I'm allowed to go and write down this thing. Okay. So what would be an example of this? I don't know. If unicorns were real, what might I deduce if I was assumed that unicorns exist? That's right, unicorns. There exists some unicorns. The backwards E just means exists. That's not how you spell unicorns, is it? No. Right. If there exists some unicorns, what might I prove from that? Come on, give me a simple conclusion from the existence of unicorns.
Magic is real.
Magic is real. Okay. So let's accept that argument. Yeah. Does everyone agree with that inference? If there exists some unicorns, therefore magic is real. All right. So do you want to make another deduction? What else could we conclude now that we've proved that magic is real?
There's I want to overcomplicate this. There's other magical beasts that exist.
Gandalf is real.
There's a set of yeah. So if magic is real, humans can use magic.
Okay. So how about concluding I should study magic then? Right. If unicorns exist, magic is real. Therefore, I should study magic because it would be a useful thing to go and learn about. Yeah.
Yeah. Or you could study magic, because I think in order to say that you should study magic, you also have to introduce you. So saying that you could study magic.
Yeah.
No, I'm not going to think about that.
Yeah. This isn't a formal symbolic proof. This is about magical unicorns. Yeah. Okay. So let's assume we have some more powerful logic that includes you and the concept of should, because we've already assumed we're allowed backwards E's, which we weren't going to do today anyway. Okay, Philip, this is just an example of a supposition. Okay, I've made a supposition. I'm supposing, so you read this bracket as suppose. Supposing unicorns exist, therefore magic is real, therefore I should study magic. And I'm going to close the supposition there. Okay? When I close the supposition, I'm now back in the real world. So I'm not assuming that unicorns exist anymore. I was only doing that inside the supposition. Okay, I'm now going to invoke the rule of implication introduction. Okay, and this rule allows me to conclude a new theorem. It says, I'm going to use this. Yeah. Okay, so I've invoked the rule of implication introduction, and notice the theorem I've now obtained below the line does not depend on any suppositions. This is a true theorem. Now, it's a true theorem in my world, in the real world. Okay. This theorem, you can roughly read it in English as, if unicorns exist, then I should study magic. Or you could read it as, the existence of unicorns implies that I should study magic. But the point is, this is a real theorem. It is based on what Hofstadter calls fantasizing or supposing. You're assuming briefly that something exists in order to draw an implication conclusion from it. But you don't actually need to assume that unicorns exist in order to prove the theorem. You just have to suppose that they exist temporarily. An equivalent notation for this, which we will make more use of, is this thing down here. This symbol means exactly the same thing as this notation. So you read this little thing as proves, okay? When you see phi proves psi, you read it as phi proves psi. And all that means is, if I was to suppose phi, then I could conclude psi. Now notice, this proof symbol isn't part of the grammar. This is not part of the logic. This is a metalogical symbol. As is the line. You know, this line is not part of the logic. Yeah, the line is part of the meta level notation that we're using to describe what the logic is. So this symbol has the same kind of status as the line. Okay, and it has the same status as these little dots and these little square brackets. Whereas the symbol at the bottom, that symbol is part of the logic. Actually, we didn't originally define it because we said we could create it out of the other symbols, but we could have defined it. We could have chucked it in as part of the grammar in the first place. So this is a really important distinction, right? This is a metalogical premise. This is saying, using the whole logical system, you can somehow get from phi to psi. Whereas the thing on the bottom is just a string of symbols. This is the phi symbol, and it's this little arrow symbol, and it's the psi symbol. And it can be difficult to understand the difference between them, because in most logics they're going to occur at the same time, precisely because you have this rule. This rule says that if phi does prove psi, then you're always allowed to write down these symbols. So it's tempting to think that this arrow actually means the same thing as the above case, because they will usually occur together. But this thing is a metalogical fact about what's going on in the logic. This is the condition that phi can actually prove psi, and this thing is just a string of symbols that you're writing down and calling it a theorem, because you have the rule. So look, right arrow is a symbol in the logic. Proves is not a symbol in the logic. It is a human abbreviation for this supposed, therefore, metalogic. Okay, I promise you another OR rule. If you remember, we got rules for introducing and eliminating and. We did all of those, and we only had 2 of them for introducing OR. So let's do the other half of OR. So this is how you get rid of an OR symbol. So anyone want to try and explain this? Take a minute to look at it and see if you can explain what this is doing. And remember what this thing is. This thing's proves.
Yeah. So this is saying, if phi or psi, and not and, we also know separately
good use of English.
What's the X symbol in Greek?
That's a chi. It's a Greek letter chi.
Chi.
It's the same symbol that appears in the LAClecture program. The LAClecture is not called latex; it is called LATEX because that symbol is a Greek lettered chi. Which is like
it really? Oh my
Yeah.
God. I've
As is
always just
the-
used /LaTeX to print LaTeX, and I never thought about it.
As is
So-
the archive. If you ever come up, there's a well-known academic website called Archive, and again, this is meant to be a chi. It's like a library. It's an archive, so it's always called Archive, never Arxiv. Archive later. Anyway, yeah.
Yeah, well, my mind's just been blown a little bit. So on the logical side, so if we know that phi or psi, but separately we've also been able to prove, or a given that there is a proof that phi gives a proof for chi, and psi gives a proof for chi, then we can say that there is chi, that chi is a valid theorem.
Good. Yeah, you have to be really careful with English. What you don't want to say is if phi and psi and phi proves chi and psi proves chi. You don't want to put English ands there because we're not talking about the logical symbol. So you did very well there. Yeah, you're saying if we've proved that as a theorem and we've also proved that as a theorem and we've also proved that as a theorem, then we're allowed to have that.
We also can't say that chi is true. It's just it's a true theorem.
Yeah, absolutely. Because like this is based on a supposition. This is based on supposing. What should we have? Phi could be unicorns are real. Yeah. And what could psi be? Think of something for psi.
Dragons. Dragons are real.
Just dragons, yeah. Dragons are a good compilers animal. All right. And I don't know. This could be there exists magic. Yeah. I think that's going to make sense. Yeah. So this inference then says, if we've already proved that either unicorns or dragons exist, we've already done that. If we've also got a proof that unicorns existing would make magic exist, we've also got a proof that dragons existing would make magic exist. Right? We've got all three of these things already proved, all sitting in our list of theorems, our theorem collection. We are then allowed to add a new theorem to our collection which says magic exists. Okay. So look, these things are non-controversial. Okay, we'd accept these in the real world, I think. Yeah, if this is saying if you could prove unicorns existed, then you'd end up getting magic existing. So I think we believe this in the real world, and we believe this in the real world. This is saying were dragons to exist, then magic would also exist. So the controversial part is this. This is a claim that either dragons or unicorns do in fact exist. Yeah, that's what we'd probably challenge in this info. Okay, good. So we haven't yet dealt with negation. Okay, we've talked about and or and implies. So we now want to introduce this concept of not X. And to do this, we have to introduce it along with another symbol, which is this thing. And syntactically, this symbol is called bottom. Okay, it's sometimes paired with this symbol for top, which not coincidentally looks like the letter T for true. So the idea is bottom is in some sense the opposite of some concept of truth. It's truth that's been turned upside down. It is sometimes pronounced as falsum. That is giving the symbol a meaning. Okay, that the symbol is just called bottom. That's just 3 lines written on a piece of paper. Falsum is assigning it a particular meaning. And roughly that meaning is going to be something like the paraconsistent contradiction state that we've talked about before. We've talked about logics where things can be true and false, and they can also be neither, or they can be both. So bottom is rather like this both state. Basically, if you manage to prove bottom, then you have a problem. If you're able to get it as the result of an inference, it indicates that something has gone wrong. You should never get into this state, but sometimes you have to consider the existence of it for a while, at least. So we can give it a meaning under natural deduction by introducing these rules, okay? And the basic meaning of it comes from its elimination. This rule says if you can prove bottom, then you can prove anything. So in this case, phi is a free variable. This could be anything at all. This could be unicorns real. It could be 1 + 1 = 3. Absolutely anything. So this is a basic rule of natural deduction. Okay, it's one of the starting rules that Gensen gives you. And people argue about this. Gensen here is trying to capture what he thinks human reasoning is like, and that's all there is to it. So some humans will debate this rule. Some humans would say if you can prove one contradiction, it doesn't actually mean you can go off and prove anything. So if you were able to prove that unicorns exist and unicorns don't exist, that clearly shows you have a problem with unicorns, but it's not obvious why you should be allowed to conclude that 1 + 1 = 3. So that there are arguments for and against the use of this rule. But Gensen has chosen it because it happens to line up with how a lot of people end up reasoning if they really think about it. But that there are logics where you take this one out. You try and do without the thing. So yeah, bottom roughly means contradiction. It roughly means you've got yourself into a state where you have proved both X and not X, and therefore, by definition, you can then go and prove anything. And this basically means you have a problem, which you're going to have to go and fix. There's been a bug in your logic. It's a little bit like getting a nan as a result of your arithmetic. Yeah, nan is defined as a symbol in floating point arithmetic. Nan stands for not a number, and it occurs if something's gone wrong in your arithmetic calculation. So why do we want to introduce this crazy bottom thing? It's so that we can give a sensible description of negation. And we want to introduce the not symbol. Okay, so the rule we saw at the top, that's how you get rid of a bottom symbol. If you've proved bottom, you can then go and derive anything from it. You can write down whatever theorem you want. Unicorns exist. This is how you can introduce a bottom symbol. So if you've proved a load of theorems and none of them have bottom in, and you would like to introduce a bottom, that is a typo. That should say that's the bottom introduce rule. I'll fix that on the PDF for you. This is the bottom introduce rule. So you're allowed to introduce bottom if you've proved phi and you have also proved not phi. You've proved that unicorns exist and you've also proved that unicorns don't exist. So you now have a contradiction, you've made a mess, and this rule says you may now write down bottom and add it to your theorem collection. And like a nan, this is an indication that you've made a mess somewhere, which you're probably going to have to go back and fix. Okay, so now we've got rules for eliminating and introducing bottom. We'll use those to understand negation now, the not symbol. So Can anyone explain this? We've actually seen this before in a different form. This is kind of tricky, but we've used it in several arguments already in this module.
So we're saying if phi can prove that there is a contradiction, then we can also say not phi. See, I don't exactly follow this because it seems like I might have a misunderstanding of what it means to be able to prove a contradiction.
Good. So it's roughly what we mean by proof by contradiction. So do you, where have we seen this? Say when we did Turing machines and uncomputability. So phi in that case were the things we suppose. We said suppose that every function was computable and that we could write them down in a big list. Yeah. So we supposed that was possible, and then we did some thinking and we ended up in this contradictory situation because we thought we'd found a number that wasn't in the list. Yeah. So we were now in a state where we'd said every possible function is in the list, and we proved that there's a possible function that isn't in the list, and you now have a contradiction. You've now reached bottom. And so from that we concluded that the thing we'd supposed must be incorrect. We said therefore it's not possible to make a list of all the functions in that way. So yeah, if you suppose something and derive a contradiction from it, it tells you you were wrong to make the supposition, and therefore you've proved its negation.
Yeah, my misunderstanding here was by saying phi, the assumption that phi was true in like a meta sense. So what we're saying when we say phi there is assume phi is true, and then if we can go through a series of proofs that lead to a contradiction, then we can say that phi is false, rather than saying at the outset that phi is correct. We're not saying that phi is correct, we're assuming that phi is correct.
Yeah, well, we're supposing, yeah? We're saying if we were to suppose that phi was correct, then we'd end up with a contradiction. Therefore, phi cannot be correct. Yeah? Well, you can write it out in the other notation. You can say, if I was to suppose phi, I would end up with bottom. Therefore, phi can't be correct. Okay. Well, if I make that supposition, and if that leads to getting contradiction, then phi must have been wrong. So we have to rule it out. Okay, and then the last one is easy. Yeah, I don't think anyone would argue with this. Well, we almost did earlier. Yeah, you said, what did you say earlier? You don't not understand.
Yeah, it does not make sense.
So at least in Genson's version of natural deduction, not phi is equivalent to phi. So symbolically, if you've proved that, you're allowed to add phi to your theorem collection. So again, people will argue with all of these rules, I think. There are other logics that have been proposed. So the philosophers enjoy this in particular. They'll take one of Genson's axioms and say, what will happen if we drop this thing? What if you having a contradictory belief about unicorns doesn't actually let you prove 1 + 1 = 3? Yeah, which is actually a good point, because you probably have a lot of contradictory beliefs. You can probably convince yourself that Joe Biden is great and also that Joe Biden is not great. But just because you're confused about Joe Biden doesn't mean that you believe 1 + 1 = 3. And humans actually seem quite happy to contain contradictions in certain parts of their knowledge without letting them flow out into everything else. And if you like this stuff, this is the basis of the TMS system I mentioned before. This is my favorite AI invention ever from 1979. This was the truth maintenance system, and it's a theory of how to do that. It's a theory that is based on throwing out this rule and saying what happens if your contradictory beliefs about unicorns and Joe Biden are just kept in a little box, and everything else you believe can go on being consistent in some sense. So here's something you might want to do in the workshop later on. We've given you all the rules of Genson's natural deduction now across those four slides. From those rules, you can now go off and derive additional rules. So these are rules which follow from the rules you've already been given. If you can question from Matthew.
Hello, is that modus tollens incorrect? I think that should give not thigh instead.
Let's think. Quite possibly. These slides are all pretty alpha. So phi implies psi, and psi didn't happen. Yeah, I think you're right. Yeah. Does everyone agree? Everyone agree there should be a not there? So if an explosion causes a bang, and there hasn't been a bang, therefore there was no explosion. Yeah. Sounds good. All right. Nice one. I will get that fixed on the PDF again. Someone's paying attention. Good people pay attention. So yeah, these rules. Let's talk about their status. These are not rules that are put into the system. So we're actually overloading the notation a little bit. Normally when we write down this notation, it means here is a rule, so you can go and use it. What this actually means is if you were to begin with those inputs, not psi, this actually means you could go through a whole bunch of inferences. You could make a proof, and you would end up with that not psi at the end. So this is a little bit of a notation overload. Yeah, this is a result. It's a result of doing a great big inference. And you might also want to write it maybe as, let's put the two things at the top and nothing done with a little comma. You might want to write it as those things prove the thing at the bottom. So again, this is meta logic. Yeah, that prove symbol isn't a symbol of the grammar. It's something that you've done with the logic. But as long as you're happy with that notation, these then are four things that you can try in the workshop to show are derivable from the basic rule. And you might have come across these before. Notice that this proof by contradiction is almost what we saw before. It's got the not signs the other way around. So normally when you do proof by contradiction, you're trying to actually prove a thing. You're trying to prove phi rather than disprove it. So this is a fairly easy consequence of the basic rule we saw, but it's swapped over where the negation sign is. And you've assumed it's opposite when you prove the thing you actually wanted to prove. This one is controversial. This is extremely controversial when we get to Gödel's theorem and modern logic. So this is a theorem. You can derive this from all the other rules, and it says for any psi, like phi, this phi, yeah, F, as in philosophy. You can make any claim you want about the state of the world, and either it's true or its negation is true. Yeah? Yeah. Either there are unicorns or there aren't. And this is used in some logical systems. This is used as an axiom. In natural deduction, you can derive it from the stuff we've seen already. In particular, you're going to derive it from some of the controversial rules we've seen already. So this was the foundation of Aristotelian Greek logic. A or not A is just given as an axiom in Aristotle. And for 2,500 years, everyone assumed that that was just so obvious that it could just stay there. And it's only when you get to modern logic that it is starting to be challenged. Yeah? And it gets challenged by things like the Gödel statement. Yeah? A statement like "this sentence is false," or you cannot prove this sentence. These kinds of claims don't seem to have a nice truth value that fits into here. But under natural deduction, you certainly can derive this, the law of the excluded middle. We'll stop for tea in a minute. Just before we go, as a contrast to natural deduction, there are other ways to set up propositional logic. So when we talk about propositional logic, we mean all the logic that is generated by the grammar we saw. And natural deduction is one particular set of rules you can use to make a proof theory. There are others. Some of them are equivalent to natural deduction, and some of them are actually different. Like if you challenge those laws of the excluded middle and so on, you get a different logic. But without going into that stuff, there are other ways to end up with the same logic as natural deduction, but using fewer rules, which, depending on your point of view, is either simpler or more complex. So, for example, here is one way of doing that. We're going to replace all the rules that took us 3-4 slides to get through. In this case, just with 1, 2, 3, 4 fairly scary looking rules full of implication arrows. So when you do this, now you have in one sense this is a better system because it has fewer rules. It's simpler. So as Gary was talking about with his proofs, you like things to be short, and short is simple. So having only 4 axioms is meant to make life easier in some cases. The downside of this is that you've completely lost any sense of human intelligibility. So the natural deduction rules are designed to be as humans actually think. They're simple steps in inference that humans tend to use, whereas no sane human would use this in their own psychological thought process. So, why would you want to do this? Anyone? Why would we want to use such a simplified system?
Well, if we're not using a human, then it might be easy to reduce and conclude different aspects of the logic with simpler rules.
Yeah, so if we're going to do stuff on computer, we don't care whether the rules are human understandable or not. We just want them to be nicely computable. So yeah, if you're going to build an AI system, an automated theorem proving system, it may be a lot easier to convert everything into this form because now you've only got 4 rules to worry about. Good. The other reason is for doing the meta logic. If you want to prove stuff about propositional logic, if you do it with natural deduction, you've got about 12 rules that you have to deal with. You have to prove something about every one of those rules to show that it's true for the whole system. Whereas if you've only got 4 rules, now you've only got to do 4 pieces of work when you're doing the meta logic. So, one person's simple is another person's complex, and this comes up all through logic and computation. Like the lambda calculus. Lambda calculus is very complex to actually express programming as a user, but it's very simple to do the meta logic about because it has so few rules. So yeah, this is just one.
Sorry.
No, go ahead.
My question is: are the S and the K here the same as the S and the K in S and K combinators?
I was just wondering that this morning.
They look very, very similar, like syntactically.
Quite possibly, yeah. Okay, homework question. Yeah. Why are they called S and K? I was trying to find that out this morning, and I couldn't actually find it anywhere. yeah, it's suspicious, isn't it? There may well be some relation. Don't know which one would be named after the other. Which came first? Yeah, have to check. So yeah, they're generally known as Hilbert-style proof systems. So remember, Hilbert was the guy who wanted to sort out mathematics and turn it all into logic and make it perfect. You know, he wanted mathematics to be able to prove itself, and then it would all be done, and we could all go home. And you know, he was definitely focused on the meta logic, and hence was interested to use these systems. They're almost equivalent to what Frege did. If anyone made it through any of Frege's bizarre Victorian graphical notation, so he didn't use these symbols, but he used the same idea of doing everything in terms of implication, rather than in terms of Boolean ands and ors and nots. So sometimes you'll see it called a Hilbert-Frege style proof system. Good. So that's proof theory. Okay. Remember, propositional logic is the main thing. Proof theory is about having rules to create theorems out of previous theorems and not thinking about what they mean. Proof theory is a syntactic approach. And there are different ways to set up the proof theory. One of them is natural deduction. Another one is these Hilbert-style methods. You know, other ways could include arguing about some of the assumptions in natural deduction, like the philosophers do. You might want to weaken some of the rules. If you do that, then you end up with a slightly different logical system. Let's have 10 minutes for a cup of tea. We'll come back and talk about the model theory at 15:55. Welcome back. Everyone still here?
Hello.
Good. Right. That was proof theory. So remember, proof theory is about syntactic manipulation. All those theorems are just strings of symbols and they don't mean anything yet. You've just got a bunch of rules. You turn one string into another and you call it a theorem, as we did in my U system. So when we come to model theory, otherwise known as semantics or representation, maybe depending on who you're talking to. I think it's semantics in the reading I gave you. Here we're going to talk about what the symbols actually mean. Okay, what is meaning? How do we define meaning in a rigorous way? And this is what makes logic actually useful, because ultimately you can do all this symbol manipulation, but it is supposed to mean something and tell you about something in the world, such as whether your CPU design actually works or not. Okay, so let's define some terms carefully when we do this. Let's define a structure as a mapping from formulas to interpretations and assigning values to those interpretations. Formulas are sometimes called sentences. I think that's why we have an S here. So we know what a formula is. It's a string of symbols. If we've derived it from the axioms and the rules, then it's also called a theorem. If we've only derived it from the grammar, then it's a formula. So a theorem is a formula with a proof. But here we're going to take any formula, not just theorems, any formula, and we are going to create a mapping. And so that mapping takes us to a set of interpretations. So now we have to define these terms then. An interpretation means you're choosing something else. This can be things in the real world, or it can be other logical constructs. And you're going to assign every possible assignment of each variable in the formula. So if you have a formula like x and y, x could be a bunch of things, y could be a bunch of things. When you make an interpretation, you're choosing one thing, one value for x to be, and you're choosing another value for y to be. So in some cases, those values could be actual physical things. Usually they are going to be truth values. So I think all the logics we're going to talk about, the ultimate values are going to be Boolean values of truth and falsehood, or true and false, written in English, not as the letters T and F, which are going to be something else. So if I write down a theorem, I don't know, all x are of x. This is first order logic, but you've seen bits of this before, right? Is this statement true or false? Well, it depends what x actually is and what r is. So if x is going to range over 3 people and 2 of them are short and 1 is tall, and r means is short, then the value of this is false. But if you choose a different value for r, such as is a person, now you're saying all x's are people, then you have an interpretation that is true. So usually we don't map things directly to physical objects. Usually we want to map things ultimately to these Boolean values of truth and false. And an interpretation is an assignment of terms within the formula that are going to help us to do that. Okay, so think of, here's your formula. We're using S for a formula. So the structure is this mapping, and it considers a set of interpretations, I, and each one of those interpretations gets a value, which can be true or false. So this will make more sense when we see some examples. I'm actually not going to go through the MIU system because it's a little different from the others. So let's go straight on to the propositional logic. So for example, okay, here is a formula which we can read as P and not Q. Okay, P and Q are variables. They're defined as variables in the grammar. If you remember, the first rule of our grammar says a variable is a bunch of letters from A to Z. Okay, so when we create an interpretation, we're going to pick a value for each of these variables. And we're also going to pick a value for the result of combining them. So in propositional logic, we can use Boolean algebra as the structure. So Boolean algebra is now introducing these symbols T and F. And these are distinct from the truth and falsehood of the interpretation as a whole. At this level, these are still just more symbols. Okay, we're creating a meaning for formula by mapping them to the symbols T and F at this stage. So there are several possible interpretations. Okay, let's consider these four first. So this is what is called the truth table that you've probably seen before somewhere, like in digital logic. And this is only showing the interpretations which are true. Okay, so if P has symbol T and Q has symbol T and P and not Q has symbol T, then we're happy. We want this to describe a world that is actually possible. So we call this true. This interpretation is true, written in English. So this line of the truth table is one interpretation. Okay. This line of the table is another interpretation. Another one. So this truth table has four interpretations written down. Remember, an interpretation is assignment of values to the symbols. So we've assigned a value to P, we've assigned a value to Q, and we've assigned a value to the expression as a whole. And the ones we've written down here are all the ones which we want to be true. We're going to define truth in this way. So here's another interpretation of those symbols. Okay, we could have, here's the same P and not Q. I'm trying to come up with an interpretation that is actually false. So what if we assign the symbol F to everything? Okay, so from the view of Boolean logic, this is incorrect. Right? If P is false and Q is false, then P and not Q. So P or not Q is supposed to be true. So this is incorrect. So we write this in English as the word false. This is an interpretation that is value false. Okay, so if I pick values for these three things, P, Q, and the expression as a whole, I'm going to pick particular assignments of the variables to T and F, and if I get the ones that I like, that I want to represent what actually happens in my part of the world, then I'm going to call those true, and that's that's the value of this interpretation. If I pick assignments for those expressions that don't match my physical world, then I call that a false interpretation. So again, this can really seem like overkill. It makes more sense when we get to other logics. Does any of this not make sense? Because it barely makes sense to me sometimes.
I have a question. This might be something that we'll talk about later, but given that we have this differentiation between valid and invalid interpretations, so models and not models, can we reason about what that means if we make interpretations based on things which are and are not models? Is that hitting into metalogic at that point?
Yeah, okay, so if I consider this interpretation, right, FFF, so this, I'm allowed to have that as an interpretation, right? An interpretation is just any, let's get the words very correct, it's any assignment of these symbols to the variables. So you're picking T or F for each of the three expressions. So yeah, this is an interpretation, and so is this. You don't like this interpretation. It doesn't correspond to anything in the real world according to your intended meaning of this symbol. So we can choose which interpretations are going to be true and which are going to be false. And our choice of which we consider is what defines true and false, these English words. So you can pick whatever you like. You could define that as being true. You'd end up with a very different kind of representation. You'd be talking about something other than the normal world that we live in. But by picking your truth and false for particular interpretations, you can make your formulas match up to what you actually see in the real world around you, so that your logic actually means something useful. Okay.
Good stuff.
Yeah, it's tricky at this point.
So I think a lot of the difficulty comes from, so once you're able to separate the fact that an interpretation is just, again, once you have pre-theory, you have the syntax, then you can kind of think of interpretation as like mapping that syntax to another syntax. And then when you actually go about assigning values to the new syntax that you've just formed around it, that's the point at which you have meaning. But it's not a syntax at that point, because we're actually deriving things from the syntax, so it's actually semantic. So it's not a syntax. It's meaning.
The tricky bit is the structure is this whole thing, right? So in this case, Boolean algebra is the structure, and Boolean algebra is this whole idea of having symbols T and F, and that every expression is going to get given one of those two symbols T and F. Right? That's what gives you Boolean algebra. So you could interpret these things completely different, right? You could interpret P to mean that red car over there, and this symbol could mean cheese, and this symbol could mean eggs, and this could mean a customer. And the interpretation of this whole thing would mean the customer in that car over there would like some cheese and eggs, please. That's an entirely different structure. So in choosing Boolean algebra as the structure, we're saying we're going to use this notion of possible assignments to the variables. Everything is either going to have a T or an F, and they're going to be combined in certain ways, and we're going to choose certain things to call true and other things to call false. So there's three levels of this. The structure is we're going to choose Boolean algebra. An interpretation is any assignment of expressions, in this case to symbols, to the symbols T and F. You could assign them to anything, cars, people, cheese. And then a value is the English words true and false, and we're going to choose which interpretations to call true and which to call false, and that defines what truth and false actually is in this system.
Yeah. So if we're actually to go about playing with each of those different levels, so we could say we could change the syntax, and that would take it from maybe Boolean algebra to something like the logic gates and kind of Regis syntax for that kind of thing. But then when we go about mapping that syntax to an interpretation, so that interpretation is then saying something along the lines of, I understand how to get from interpretation to value. So yeah, that interpretation is kind of this abstract field, I guess, where you're taking a syntax and then you're putting a symbol next to that syntax. But then if we were to go about changing values, you could talk about the difference between, so one interpretation of the value is it's true, one that it's false, whereas another interpretation might be on my machine, rather than saying true or false, we would say high or low, and that would be a different set of values. Is that correct?
Yeah, so you could have an interpretation of high and low voltages if you're trying to understand this formula as a physical piece of digital logic. So yeah, technically you don't need to consider these symbols T and F in your definition of a structure. A structure is just something which takes a formula as an input, and it maps it to the collection of which interpretations are true and which are false. I guess in functional programming you'd write it as something like the structure gets mapped to a mapping between assignments to values. I guess that's the overall structure of a structure.
Yeah, that makes sense.
Yeah. So in this particular case, we've chosen these little symbols T and F, and our assignments are ranging over T's and F's, and our values come out as English true and English false. But we could have assigned things completely differently to things that aren't T and F symbols, to real physical objects, for example. And we could, I think you always have to have English true and false coming out. Or at least in all the logics we're going to look at, you've always got English true and false coming out. And intuitively, the English true and false here mean that the world could actually be in the case being described by the formula, right? If you have a simple formula like x and y, okay, there is one interpretation of this where x is t and y is t, and the whole thing takes value t. And that's something that could actually happen. You could be in a world where the car is red and the sky is blue, and it's also true that this expression has value t. All three of those things are occurring together in the world, and the world could be like that. But you can't be in a world where the car is red, the sky is blue, but this expression doesn't have the assignment t. You're saying that world just can never take place, and that's what gives meaning to the notion of andness. You're going to define all of these symbols according to their interpretations and their model. So yeah, again, this is a very common pattern throughout logic. You've always got two versions of everything. You've got a version inside the system and a version outside. So T and F are assignments that occur inside the structure. T and F are things that Boolean logic is doing internally, whereas English true and false are outside of that system. This is us saying some of those possible worlds are actually physically possible, rather than just syntactically possible. And that's how we define meaning. We're saying some syntax leads to interpretations which could actually occur in the world, and some cannot. So this may get clearer if we look at some extensions of that idea, possibly. English true and English false are values of one particular interpretation of the formula. Right? We take each expression, we assign these T and Fs to them in the case of Boolean algebra, and we say, is that true? Actually, you might want to compare it with arithmetic. Actually, let's go back. Consider an arithmetic version of this. Let's say you have an expression like 3 plus minus 2. Okay, so I've chosen that to have the same structure as this thing. Consider what values, or rather what assignments these symbols could take. The number 3 is going to get assigned to something, and the number 2 is going to get assigned to something, and then this whole expression 3 plus minus 2 is going to get assigned to something. And if the number 3 is assigned to, if the symbol 3 is assigned to 3ness, and the symbol 2 is assigned to 2ness, and the result of this is assigned to oneness, I guess it's called unity, then that would be a true interpretation. We would define truth to be that. If you assign that symbol to 3 and that to 2 and this to 4, that would be a false interpretation. So the Boolean algebra is
that's really good.
Yeah, Boolean algebra is one algebra. What is normally called algebra in high schools, as in the algebra of possibly real numbers and addition and multiplication, that algebra forms a different structure to Boolean algebra. Because what Boole did was to show that the structure of Boolean algebra is very closely related to the structure of arithmetic, because you can almost interpret that as a piece of arithmetic, can't you? How would you write that as arithmetic? When you've got an or, you've got a plus, and that would be 1 minus q. So here you're going to interpret p and q as the numbers 0 and 1, and that's not quite plus. Yeah, you have to fiddle your plus so that 1 add 1 makes 1 in Boolean algebra. But it was Boole who made that connection between the algebra of what is now called Boolean logic and the algebra of numbers in arithmetic. Okay, so we're now happy that a formula can have many interpretations within a structure. So assuming we're going to work with Boolean algebra as our structure, let's consider some cases that can occur. Okay, in some cases, have we defined a model yet? Let's use the word model to mean an interpretation with value true. Okay, so that's all it means. A model just means interpretation that happens to be true. Makes the language easier. So in some cases, all possible interpretations are models. So consider this. Okay, this is actually a theorem. So theorem means something you can prove using the proof theory. So you can probably convince yourself that all possible interpretations of this within the structure of Boolean algebra are in fact models. So if you want to make a truth table, you've got x, y, and then you've got the whole thing. I'm not going to write the whole thing out. You know, what are the different values of true and false that all these things can take? And what you'll find is that every possible interpretation comes out true. So there's no possible world where this doesn't work. Okay? So any physical world where there's two things called x and y, if x is true and y is true, then it must be the case that y is true and x is true. So this is called a tautology. A tautology is different from a theorem because a theorem is a proof theoretic concept. It means we prove something from the rules using proof theory. A tautology is a formula whose interpretations are all models. So in every possible world, the thing is true. So the opposite of a tautology is an inconsistency. This is where there are no interpretations that are models. So for example, this thing, this is also not a theorem. So at least hopefully you can't prove this. If you can prove this from your logic rules, then something's gone wrong with your proof theory, right? So there's no way you can pick values of x and y. You could go through every combination of x and y, true, false, true, true, false, false, true, true. And there just won't be any combinations that makes the whole thing actually work. So this can never occur in its intended meaning. So we call this an inconsistency. It's the opposite of a tautology. Whereas probably most formula are going to become contingencies in the model theory. That means there are some interpretations that make them true, and there are others which make them false. So for example, if we just give you this, x and y here are free. They're both free variables. So you know, there are now 4 possible worlds. You know, x and y can be true, 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 false, 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 true. And in one of those worlds, where they're both true, the expression is true. And in the other worlds, it isn't. So these are different concepts from proof theory. In proof theory, you can say something is a theorem, or you can use meta-logic to prove that it's not a theorem sometimes, or in some cases you just don't know because you haven't found out yet. In model theory, you can have a tautology where every interpretation is true. You can have inconsistency where every interpretation is false, and contingency means maybe. There are some possible worlds where the thing is true and others where the thing is false. So, you know, a contingency plan is what you make when something might happen, but you don't know if it's going to happen or not. I suppose you could go on and define a tautology plan to be a plan that you're going to execute in every world, and an inconsistency plan for a plan that is never going to be executed, if you wanted to. We make a lot of plans like that in university management. So to define the values of Boolean algebra, then, you know, this is defining truth and false, the English words, in terms of the structure that is Boolean algebra. We can define Boolean algebra's values through these truth tables. So these are what you've seen before in digital logic and AI, probably. Maybe you've not seen these ones before. This is the bottom symbol, you remember. The bottom means something's gone wrong, and we need to give a value to that symbol as well. So we're just going to define that as always being F. And we're going to define this top symbol. This is a 3 lines drawn on a piece of paper called top. This is T in Boolean algebra. if you put all of these tables together, then you can combine them because phi and psi can be any expression, so you can join expressions together arbitrarily, as you do in the proof theory. And this will allow you to assign a truth value to any formula that you've constructed from the propositional logic. Or you're assigning a truth value to each interpretation, and then you can assign these other statements to the formula as a whole. You can say whether something is a tautology or inconsistent or contingent. These are properties of the formula as a whole. A truth value is a property of a particular interpretation. So when we give a truth table, like you might have used in digital logic, what these actually are completes of models. These are all the models for phi and psi. Okay, so that's 4 interpretations that are all true, and we don't show any of the false interpretations. Okay, that's the set of possible models for the implication symbol. Yeah, so as always, if you've proved this bottom symbol, you have a problem. Okay, and if you've proved T symbol, this is just defined as something that is always true. So sometimes you might use this as a starting point. You just assume true before you've done anything, and you see if things continue to be true as you go along. So we've seen the proof theory is about syntax and proof. And we've introduced this notation that says if you can use the rules of proof theory to get from phi to psi, you're allowed to write down phi proves psi. Okay? That means that psi is derivable from phi using the rules of proof theory. If you can derive psi without assuming anything, then you can write this. You can write nothing proves psi. So this means psi can always be proved without making any assumption. So in particular, this means that psi is a theorem because it is always provable from scratch. In this case, psi isn't necessarily a theorem. It's only a theorem if phi is also a theorem. So these are notions from proof theory. The notion of proofs and the notion of being a theorem, they come from proof theory. Model theory is like a mirror image of proof theory. It's a separate structure, but it ends up doing similar looking things, and you hope they're going to be the same thing. So in model theory, we can say this. We can say that phi entails psi if their truth tables are identical. And this is probably what you've done in computer architecture, digital logic. If I give you a big chunk of logic gates, then I say, is this equivalent to this smaller chunk of logic gates? At some point, you've probably sat down and you've created truth tables for the 2 circuits, and you've shown that every line of the truth table is the same. And therefore, you're going to argue that the 2 circuits are equivalent. And that word equivalent actually means entailment. It means all the models of psi are models of phi and vice versa. They have the same truth table. So this is a completely different concept from proof. We've not used any rules of proof here. We've only used the model theory. We've written down truth tables for them, and we've said they match. And if they match, then we can write down phi entails psi. And in proof theory, we have this concept of being a theorem. The theorem means you can prove it from nothing. If you can entail something from nothing, then that's what we call a tautology. It means in every possible interpretation, this thing comes out true. So that was proof theory and model theory. When we come to meta logic now, we're going to ask questions about those theories. And in particular, the obvious question is, how do they interact with each other? Because we've now ended up with these two entirely different concepts of proof and entailment. And we probably talked about this in computer architecture, because usually half the students in that class will show my circuits are equivalent by using entailment. They'll write down these truth tables and show the two circuits have the same truth values. And the other half of the class will use proof rules, maybe stuff they've learned at school, maybe stuff from a book or even from one of my slides, but there are standard tables of proof rules for what is at that point called digital logic. And at the level of first year architecture, it's not obvious what is the relation between these things. You know, it's actually quite magical that everyone comes up with the same answer, whether you're doing it the entailment way or the proof way. So, you know, the big question in the meta logic is, can you understand why these two completely different theories end up giving you the same results in propositional logic, at least. So, you know, natural deduction or any proof theory defines provability. Okay, when you do the model theory, if you put in a Boolean algebra structure, you get entailment. These seem to be two completely different definitions, roughly corresponding to our English word truth, which is very much put in quotation marks there, because we now really don't have a clue what it means anymore. You know, and versions of this, special cases are that you might get a theorem coming out of the proof theory, or you might get a tautology coming out of the model theory. And, you know, wouldn't it be nice if they matched up? Okay, wouldn't it be nice if they were completely equivalent? Because then it wouldn't matter which one you used, and then all the first years would be correct regardless of how they did it. So matching up actually includes two directions, right? The first thing is, we hope that if you can prove something, you can also entail it. Okay, this means if you can use the rules of proof theory to get from phi to psi, it would be nice if you could also use the rules of model theory and entailment to get from phi to psi, and we call this soundness. Okay, this means your logic is sound. It means anything that your logic decides is actually true in the model theory. Okay, your proof theory has said the world is like this, and then you check it in the world through your representation, your structure, and the proof theory is correct. So that your logic is sound if you have that property. If your proof theory was able to go and prove things that didn't occur in the world, then it would be unsound and you'd have a problem. Conversely, we hope that if you're able to entail anything with the model theory, then you are also able to prove it. And this property is called completeness. So, you know, you could actually quite easily, you could imagine this not being the case. So we've seen natural deduction, for example, has loads of rules. And if you were to remove one of those rules, there'd be a bunch of things that you couldn't prove anymore. You keep the model theory the same, but you weaken the proof theory, and you now end up with there being things that are true, but not provable, because your proof theory isn't strong enough anymore. So that seems less bad in a way. Okay, being unsound would be really bad, because your proof theory is going to go around proving stuff that is false, which is a total mess. Being incomplete seems less bad, because anything you prove could still be right, but you just miss a few things. There's just a few things that you don't have the power to be able to prove that happen to be true, but you might never notice those things in everyday life. So notice we are now doing meta logic because we are using English. We're using English if and then, and this is very deliberate. I'm not writing these things as rules at this point because we're talking about the logic rather than being inside of the logic. So, you know, it would be nice if these things matched up. Okay, it would be nice if your logic was sound and complete, because then you could easily flip between those two methods of convincing yourself that stuff was true. You know, it wouldn't matter if you do the truth table way or the proof way. And you probably all assume this was the case when doing digital logic. Now, luckily for natural deduction and Boolean algebra, this in fact is the case. Okay, so propositional logic, as presented here, is both sound and complete. For other logics, this might not be the case. That's when things get more complicated. Matthew.
So is soundness the same as consistency?
No, we'll talk about consistency later. Consistency means specifically that you can't prove X and also prove not X. So I think this would lead to being unsound. This is inconsistent. Yeah, if your logic is inconsistent, then it will certainly be unsound because your model theory isn't going to let you do that. Yeah, but there are no models where this can be the case. But there may be other ways of being unsound as well. Okay, so look, when we talk about consistency, you have this special symbol, this little right-angled thing. What's that actually called on the keyboard? Anyone? It's the thing next to the 1 key on the top left. It's not a tilde.
It's not called the not symbol. Oh no, because the symbol's separate from the meaning.
Yeah. So look, when we talk about soundness, we don't have to worry about there being this special symbol. Okay, soundness is just defined through this relationship. When we talk about inconsistency, we are talking about a particular form of unsoundness, which involves a symbol like this. Yeah, so inconsistency means you're able to prove things, and you can prove the same thing with that little symbol put on the front of them. Okay, so special case.
Okie dokie.
Yeah, good.
So it can contradict itself without being incomplete, or vice versa.
So it's not about contradicts. So a contradiction. What's a contradiction? That would be a contradiction, wouldn't it? X and not X, or anything that proves bottom is a contradiction. Yeah. In the symbols we've given, that is a contradiction. The bottom, but those are proof theoretical notions. Whereas when we talk about truth and falsehood and inconsistency, those are model theoretic notions. You know, this statement about soundness says that if something's provable, then it also has to be entailed in the model theory. It's a link between the proof theory and the model theory, whereas talking about deriving contradictions is purely inside the proof theory. Yeah? So a contradiction is a proof theoretic concept, whereas a soundness is a link between proof theory and model theory. Okay.
Yeah. Okay.
Okay. Good. So look, I'm not going to go through the proofs of these in any detail. I think we've really done enough today. The proofs are given in the reading for this week. If you want to at least look over them, I wouldn't expect anyone to fully understand them. And remember, these are proofs in metalogic. These are proofs about the system. They're not proofs inside the system. So in particular, they're going to use a lot of English words, and they're going to use a lot of concepts that don't exist inside propositional logic to demonstrate properties of the system as a whole. I mean, very roughly, for anyone who wants to go and read that stuff, you've got soundness and you've got completeness. The way that soundness is proved is using what is called induction. Have you guys seen induction before? No? So roughly you pick some property of the world. You say everything is great, then it's in the way I want it to be. And every possible way of changing the world, you show that it retains that property. So this is sometimes called an invariant. You can say the world is great, and the world can change in these three different ways. You know, it could get hotter, it could get colder, or it could get wetter. But you can, if you're able to show that each of those changes retains the property of being great, then the world will always be great. Does that make sense? Let me give you the English. Right. Let's assume the world is currently great. Okay. The world can change in three ways. It can get hotter, colder, wetter. Okay. We are trying to prove, our hypothesis is the world will always be great. Okay. And we're going to do this by showing if it gets hotter, or rather, if it's great and it gets hotter, then it's still great. And then we're going to show if it's great and the world gets colder, then it's great. And finally, we're going to show if it's great and it gets wetter, then it's great. Okay. So this is called induction, and this is another form of reasoning. This is meta logic, so you probably can't do this within the logics that we've seen yet, but it's a human form of reasoning. You say if a property currently holds, and we've got a complete list of all the things that can change, and under each of any of those changes the property still holds, we can conclude, therefore the property will always hold. And that's what you're going to see in a soundness theorem. And when we talked about natural deduction versus Hilbert-style systems, this is easier to do if you have fewer rules in your system, because here you have to do 3 pieces of work. You have to prove this for each of the rules. So you might want to do this in a Hilbert system, so you don't have as much work to do. But you just have to show, remember, soundness is defined as if you can prove something, then you can entail it. So you start off with something that you definitely can prove and definitely entail. That's your starting point. And then you show that under each application of these rules, that property still holds. So here's a really simple version of induction. Let's prove that all numbers are great. Okay, hypothesis, all numbers are great. Okay, I'm going to do, let's look at the number 0, and we'll look at it directly, and we can see that it's great, and we're happy that 0 is great. And now we need to rule something like, if n is great, then n plus 1 is also great. Okay, so you're going to have to prove these 2 things. So it's easy to prove that 0 is great, because we'll just look at it and, hey, it's an awesome number. You know, it's a circle, and it represents the absence of anything. That's definitely great. Happy with that. This is a little harder to prove. Assume you've got a number that is great. Probably the number next to it is also going to be great, because it's 1 bigger. If you found a number that's great, if you add 1 to it, it's going to be at least as great, because it's even bigger than the number we've already found. So if you're willing to accept this as well, now you have a starting point. You have an induction hypothesis. That's your induction hypothesis. You have shown that the hypothesis maintains every time you move. So you can now prove that all numbers are in fact great. Okay, 0 is great. If n is great, then n is 1 plus great. That means that 1 is great because it's 1 bigger than 0. It also means that 2 is great. It also means that 3 is great, and so on. And it's the same idea here with the rules of natural deduction. You're going to show that that soundness property holds in an initial easy case like 0. And then you're going to show that if it holds at the beginning of the rule, then it continues to hold at the end of the rule. So no matter what combination of rules you apply, the soundness property will always hold up. Proof of completeness is more complicated. I have trouble with it, to be honest. It's in Huth. Roughly, it comes in 3 stages. You have to make an argument about each one. You're going to assume that you're going to show these things, and you're going to end up, you've gone from entailment to proof. The little starting point is you've got to show that this thing is a tautology. Remember, something that is always entailed is a tautology. That's actually quite easy to show. This thing is a nested implication. It can only be true in one particular interpretation. The only way, you need all of these to be true and this to be false. Sorry, it can only be false if all of these are true, and this is false. That's a typo. So with implication is quite a weak claim to make about anything. There's only one version of the world where implication goes bad. So you can consider that version of the world. You'll end up getting a contradiction. And in this pattern, this is proof by contradiction. You've assumed something, you've assumed that it was false. That got you a contradiction. Therefore, the opposite of what we assumed is a tautology, and that's going to prove the thing that you were after. So yeah, this is meta logic. This is proving stuff about the underlying logic. So it's hard. You don't need to know the details. You need to know that propositional logic is sound and complete. If you're of a certain personality, you can only convince yourself of that by working through the detailed arguments, and they're all given in Huth. Final piece of meta logic for propositional logic is to do with decidability. Right? If I give you a theorem, can you always find its proof? And the answer to this is yes. If I give you a formula, can you always tell if it's a theorem? The answer to this is yes. You have done this before. Where have you done this before?
I'm assuming with the mu system, MIU, because we could tell when a given algorithm algorithm was a theorem because it either we knew that it had to start with an M, otherwise it wouldn't work, and we knew that it had to have we knew the rules of the MIU system, and we knew that because of those rules, only certain strings, for instance, ones where you had either an even number of i's or a given combination of i's and u's, such that if you converted the u's back to i's, you would end up with an even number of i's.
Okay, good. So have you ever done this on propositional logic? Have you ever used such algorithms? You've probably done it without realizing it in digital logic, in computer architecture. It's a very common exam question. Here is a circuit. Is it equivalent to this other circuit? Or can you prove a Boolean identity? So again, it's possible to use meta logic to prove why this is the case, why you can always do this for a propositional logic formula. And you might consider algorithms that are going to parse a Boolean expression. I'm just trying to find a Boolean expression. Something like this. You might parse it. You might go and consider all the bits of that and all the bits of that, and then put them together. And you can always put it together and figure out if it's a theorem or not, either by going the model theory way or by going the proof theory way. So the propositional logic is nice because all these properties are nice, and this is what Hilbert hoped was going to happen for all the other logics, so that we could live in Hilbert's paradise where everything actually worked. Okay, there's been a lot in here. There's only 25 slides, but a lot of content. So we don't really have time for any breakouts. If you want to take this stuff home to do by yourself or to do over Easter, here's what we would have done in the breakouts. You can do somewhat. Either carry on doing your Lambda interpreter thing, or if you'd like to practice what's been in this lecture, then a nice exercise is to find proofs for each of the derived natural deduction rules. So you remember we started with the basic rules of natural deduction, and we said that certain other patterns of human reasoning can be deduced from them. So a nice example would be to go back to this slide in particular. There's a knot down there. Yeah, a nice exercise would be to look at each of these four and show how you can derive them from the basic rules of natural deduction. That's a nice way to understand natural deduction. And you should end up with, let's say you're going to do this one. You should end up with an argument, like all the other arguments you've seen. You're going to start with that, and you also have that, and you're going to derive something. You're going to derive something else. Maybe you can derive two things from something up there. Make a big proof stack and try and get the result, not phi, coming out at the bottom of it. Nice exercise. This is very optional. Don't think we're assessing this in any way, but a nice way to check an advanced understanding is write an evaluator program. If you've just written a Lambda interpreter, it's pretty simple to write a propositional logic interpreter. So you're going to take a string such as this and evaluate it. And you'll see from what we've seen today, there are two different ways of doing it, right? The easy way is probably using the model theory. You're going to evaluate all the interpretations and check if it's a tautology or not. Or, and this is harder, you can search for a proof using proof theory. Some of you have done this for the MIU system already. Can you chug through those rules and apply them in different ways and find a proof? Maybe by brute force searching, maybe by something cleverer, to try and get to the theorem. So that's advanced, but it's interesting to try at least, and it's very similar to writing your Lambda interpreter. Otherwise, we've got Easter break for 2 weeks. I'll see you after the break. We have to do these portfolio assessments. We have been working on question 2 about the Lambda interpreter. It would be nice if everyone had that finished by the time we come back, because in the second half of the semester we're going to consider question 1, the one about logic. So again, you don't need to do anything on question 1. We're going to think about question 1 next time. They're the wrong way around. The original plan was to do logic first, then computation, but we've ended up doing it this way. So it would be really nice for everyone to get their lambdas together. I'm happy to have a look at some of those before you submit them during the workshops when we come back. See if I can help with anything. Get it off your plate, and then we'll work on question 1. Yeah, as always, there's a lot of material here. This is supposed to be hard. That's what makes it fun. So don't worry if you don't understand everything. It has taken me a long time to understand everything. Well, I still don't understand everything. The whole theory is that there are things that can never be understood. That's what's going to come out of this. But try and get as much as you can. We understand this is a third-year Lincoln course, and assessment will be appropriate to the level. But I'm trying to show you as much cool stuff as I can along the way. Otherwise, have a good Easter. Any other questions? Anything?
No. That,
No, just,
how much time do you recommend we spend revising this material?
It depends how much you love it.
Oh,
Yeah,
it seems hard.
the exam questions will be of a similar style and ilk to the portfolio ones. Yeah, they're all written quite open-ended, so you're not expected to understand every little thing. You're expected to get a flavour of it for now. But
Cool.
yeah, if you can kick out a lambda interpreter and a propositional logic evaluator, that would be very nice. But if anyone likes functional programming, this is the ML book. This is written by Larry Clausen, who is the guy who taught me logic when I was a student. And there's a very beautiful lambda calculus interpreter in here, and I think there's also a propositional logic interpreter that he'll take you through exactly how to do that. But it is all written in ML, which is very similar to Pascal. In fact, probably at this level, you won't even notice the difference. The syntax is almost identical. So if you happen to like functional programming and you want the original source of where I got a bunch of this from, that's ML for the Working Programmer by Larry Paulson. Otherwise, see you after Easter.
Thank you. See you after Easter.
Cheers. See you after Easter.
Thank you very much.
Thank you.
Thank you.